This video is going to cover chapter 4. Chapter 4 is about molecules, their structure, the shapes they end up forming, and basically how we create bonds. So we talked about this a little previously. The idea that atoms don't necessarily come with an outer shell, right? On the periodic table, we had that +1, +2, +3, yada, 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 showing how far they were away from 8. Whereas +1 meant they only have 1 electron in their outer shell, 2, 3, we skipped the transition metals, 4, 5, 6, 7, 8. So what happens, if we're from that first column on the periodic table, such as sodium, what happens when we don't have a full outer shell? All elements are desiring a full outer shell of 2 if you're hydrogen or helium, or 8 if you're any other element. So what happens when we don't have a full outer shell? The element will create a bond with another element. Sometimes itself, sometimes other elements. So there's 2 different types of bonds to make a molecule. We have ionic bonds, which is the transfer of electrons from one atom to another. Column on the periodic table, such as sodium. What happens when we don't have a full outer shell? All elements are desiring a full outer shell of 2 if you're hydrogen or helium, or 8 if you're any other element. So what happens when we don't have a full outer shell? The element will create a bond with another element. Sometimes itself, sometimes other elements. So there's 2 different types of bonds to make a molecule. We have ionic bonds, which is the transfer of electrons from one atom to another. So something else that I didn't mention previously, but that this is between a metal and a non-metal exclusively. So these bonds end up creating an ion, pictured here, positive ion, negative ion, that have a strong physical attraction to each other. So although they're not sharing electrons necessarily, one's giving, one's receiving, they end up, the ions that they create from losing an electron or gaining one, create this strong physical attraction to each other. Plus wants to hang out by minus, opposites attract, and they end up basically being joined together in space and exclusively hanging out. Whereas covalent bonds, they are sharing the electrons. This is between 2 nonmetals. And so this creates bonds between the elements. I'm sorry, elements, atoms, same thing. So now they're physically sharing those 2 electrons. So right here, this picture I put up here is showing the bond depicted like this, the sharing of electrons, which is more accurate to how this physically is represented. But on paper, we would commonly show that bond as O and then the bond O. So how the heck do we make these bonds? First, we'll start out with the ionic, right? Here's a little reminder of what it is. Has to be between a metal and a non-metal. So some has to be between something on this side and this side, with the exception of hydrogen, who is actually a non-metal. So if we remember, we talked about this periodic trend, right? Where it went 1, 2, 3, 4, 5, 6, 7, 8. And this tells us how many electrons were in its outer shell. And then we talked about describing them as ions. So this is +1, +2, +3, plus or minus 4, plus or -3, -2, -1, where plus described the electrons that they desired to give, and minus described the electrons they wanted. So to create an ionic bond, they're desiring that the net charge between the atoms is 0. So when we want to create an ionic bond, we're going to be looking at this trend here, the +1, +2, +3. We can ignore the how much is in their outer shell for ionic bonds. So sodium has +1. He wants to give away 1. Chloride is a -1. He wants to take on 1. So these guys are perfect pairs for each other. Sodium has 1 in his outer shell to give away to chloride, who's only missing 1 electron. So if he gives that electron away, he now has it. And sodium is happy because although we only depict him as having 1, that's his outer shell. Underneath, he has a full shell. So once he gets rid of this outer one, he's happy because he has another whole nother shell underneath that. Oops. Chloride's happy because he's now filled his outer shell. And so, like we said, this creates a positive ion, this creates a negative ion, and they hang out together in space. I should have drawn those closer together. If we were looking at magnesium, magnesium commonly forms, he has 2 electrons he wants to give away. Chloride again is a -1. So this time, magnesium, he's like, I'll create a bond with you, but I have 2 that I want to give away, and you only have 1 spot open. Well, chloride's like, that's fine. I'll just bring along a buddy. And so magnesium, ooh, I don't know how I did that. So magnesium in its outer shell has 2. Chloride has 7. Oops, 1 too many. This chloride has 7. So magnesium's like, sweet, I can get rid of both of them. And again, he has a shell underneath. And so they create a bond and hang out together. And that's how you get the compound magnesium chloride. If you noticed, magnesium was a +2 and chloride was a -1, there's a really easy way to always be able to predict how many atoms of each is going to be needed. So I had already wrote out magnesium chloride as MgCl2, right? It kind of already alluded to the fact that it needed 2. And I showed you why it needed 2 based on showing the orbitals. But a really foolproof way of determining how much each subscript is, how much of each atom we're going to need, therefore how much the subscript, the number the subscript indicates, is to swap their predicted charges. So magnesium, if we take this -1, it would be like saying it has a 1 subscript. Anytime something has a subscript of 1, we can omit it. And then that gives 2 to our chloride. And the same worked up here with NaCl. They just both happen to have subscripts of 1. And so therefore we were able to omit them. So that's awesome, right? Well, how do we do this for covalent bonds, which are only exclusively from this part of the periodic table? Again, with our buddy hydrogen, he's included. So covalent bonds are a little bit trickier. They're not necessarily looking for a net charge of 0, but rather, something I've totally neglected to say in the last slide. Every time that, we said magnesium was a +2 and chloride was a -1, but we took -2 of those atoms, right? If we were to add +2, -1, -1, we have a net charge of the molecule of 0. So that's what they're ultimately looking for. But covalent bonds are a little different. They more so just want together to have a full outer shell. So like we said, we're working exclusively from this side of the periodic table plus hydrogen. So hydrogen's a little funny, right? He's the funny guy. He never, even though he's in this +1 category, he is the one exception. He never wants to give away this electron because hydrogen's only looking for 2 in its outer shell. It's all it can hold. Hydrogen does not have another shell underneath this. Hydrogen, if he gives away that electron, that's all he has. He doesn't have any electrons left, which is really bad. He needs at least 1, and he wants 2. So not only is he 1 away, fluorine here has a -1 charge. He is 1 away from having a full shell. So helium could give it to fluorine, but then hydrogen has nothing left, and that's really bad. So they're like, okay, we'll make an agreement. I'll let you spend some time with my electron as long as you orbit it back to me. And fluorine's like, okay, I'll let you spend some time with this electron as well, as long as you circle it back to me. If you give me some time with it, it's kind of like, reminds me of holding a hot potato when you're tossing it. Not that this is real in real life, but the hot potato game, right? When you're tossing it between 2 people, you're like, hot, hot, right? It's like, okay, I'll get a little time, but you have to take a little bit of time with it. Okay, I get it back now for a little bit. You get it back now. And so they end up being bonded because they're sharing those electrons. So it's not necessarily that they're looking for, this does happen to have their charges cancel out, but that's not necessarily what they were looking for here. They were more so looking for each of them to have a full outer shell. And I think that will make more sense here in the example of H2O. So hydrogen, again, he never, even though he's a +1, he never actually wants to physically give it away because he doesn't have another subshell underneath. So he's hanging out here with 1. Oxygen, which has a -2 charge, meaning he's 2 away from a full octet, has 6. And we already know another hydrogen is going to come into play here. So hydrogen, 1 hydrogen, basically, he could hang out here. Oops, let me draw this better. So let's make it like this. So basically, hydrogen's like, yeah, we could hang out. But I can only basically share 1 electron with you because I only have 1 to give. And oxygen's like, that's awesome, but that's not necessarily enough. And so it pulls another hydrogen in. Oops. It pulls another hydrogen in. And so now hydrogen's happy. He gets to spend a little time and share some electron time. And oxygen's happy because he has a full octet. I really should have drawn these a little bit better here. So oxygen has a full octet and hydrogen has the hydrogen version of its full octet. Okay. So there's always exceptions, right? So a fun thing about ionic bonds is that they can form another ionic bond with what's called a polyatomic ion. And so a polyatomic ion is what's listed down here in this chart. And it is ions that are made up of covalent bonds, but they don't end up as a net neutral. They end up giving off charges once they form their covalent bonds. So these are polyatomic ions. They are not listed on they're elements from the periodic table, but they're not necessarily listed on the periodic table with these names. So like hydroxide, OH-, you're not going to find that on the periodic table. So this is a list of common polyatomic ions. There's millions out there, but this is just a list of common ones. There's one more I want to add to this list, and it's bicarbonate. It's HCO3-. So this list, I'll write it on the board, I'll give it to you on a physical piece of paper. You do not need to memorize it, but I want you to be able to utilize it and understand how to recognize these names, recognize polyatomic ions. So even though these ions are made up of covalent bonds, they end up forming ionic bonds with other metals. So in these examples, I'm showing you examples with the metal sodium. Or bonds with polyatomic ions work the same way as ionic bonds, right? So if we were to go to the periodic table, we'd be able to know that sodium is a +1. But here's the thing. As I want to be able to identify that these elements sitting together, I don't want to go grab oxygen's charge and hydrogen's charge. I want to look for them on this table and be able to identify that it has a minus charge. So when we cross their charges, right, they come together. So sodium gave his 1 electron to this guy, who was looking for one. So the same thing with sodium carbonate. Sodium has a -1 charge, and carbonate, again, so it's not necessarily that you need to memorize these polyatomic ions, but just kind of like be able to recognize that it is a polyatomic ion. So carbonate, I don't ever really remember the charges. I just am able to recognize, hey, that's a polyatomic ion. Okay, so carbonate has a -2. And so, why does it say sodium has 3 here? I think I made a mistake. Oh my gosh. Okay. So here's the kicker with polyatomic ions, right? If we do our swap rule here, we still, this subscript still needs to be included, and it does not interfere with our -1. So our sodium gets a subscript of 2, and it's almost like saying in brackets a subscript of 1. But since we don't usually use 1, we omit 1 when it's a subscript, we also omit the brackets. And so it ends up looking like that. There are cases, though, when it's, let's say this was magnesium and it formed a +2 charge. Then and let's just say theoretically, carbonate had a -3 charge. So when you have a polyatomic ion and you're swapping those charges, right? Magnesium 3. Let's say we had to put a subscript of 2 on that carbonate. We don't want to just suddenly put 2 right here. That looks like we have 32 oxygens. Instead, we want to say that we have 2 carbonate ions. And so in that case, we would see parentheses. So if you ever are trying to do this backwards, basically, if maybe on a test question or OWL question, you're given this, and then you're supposed to list the ions, anything with parentheses in it is a pretty telltale sign that it's going to be a polyatomic ion. All right, so we were previously able to, do the whole +1, +2. We were skipping the transition metals, right? And then we continue +3, +4, -3, -2, -1. Why the heck were we skipping the transition metals? Well, because transition metals, their charge cannot be predicted. They are, as the name implies, they're able to transition with the amount of electrons they have. So sometimes nickel will form a +2 ion, but sometimes it'll form a +3. Sometimes it'll form a +1. And it's up to us to figure that out. Now, that might seem super complicated, but basically it's kind of like solving a math problem. So iron oxide, right? This is a metal, so this is an ionic bond. Iron is in this transition metal category. Let me try to find them. Iron, Fe. Oh, here he is. Right? Can't predict his charge. We don't know. Oxygen, though, we are able to predict its charge. It's a -2 charge. So basically, we'd be needed to be given the name or the molecular formula here. I'm going to give you the molecular formula. It's FeO. So if oxygen's a -2 and there's implied subscripts of 1 here, let's say we did the crossover, it must be equal. So in this case, iron is forming a +2 charge. So like I said, they have to kind of tell you in the name. You work backwards like we just did there. I'm sorry, the molecular formula. Or if they're writing it out, they have to tell you in the name. And that's when we see Roman numerals, right? So whatever Roman numerals come after the transition metal tells you its charge. And it's always going to be a positive charge. And so that's how we were able to get FeO. But like I said, they're transition metals. Sometimes they form +2s, sometimes they form +1, sometimes they form +3, and so on and so forth. So in this case, this name is telling me that iron is forming a +3 charge. We know oxygen always has a -2. So if I were to write out the molecular formula with the symbols and subscripts, I would have Fe2O3, right? Because I was swapping those charges. Oxygen normally has a -2 charge. Iron has, in this case, a -3 based off of the name. So now let's look at an OWL question. This is your OWL question 3. They're telling us the element and its charge, and they want us to write the compound formula. So we will do, this is specifically ionic bonds too. So we'll go ahead and do the swapping of the charges. So if I were just to write it together, I'm going to give silver a subscript of, or give that that charge as my subscript to oxygen, which is 1. And when we have 1, we just imply that it's 1. Oxygen's charge I'm going to give to silver, which is a 2. Same thing down here. Ammonium, which is a polyatomic ion. Really, you could write it like this, give it a subscript of 1, right? But we omit the subscripts, and when we omit this, I did not mean to clear that off. When we omit the subscripts of polyatomic ions, we usually omit the parentheses that come with them. So because we're giving this +1 charge to bromine and a -1 charge here, we can just write it as NH4Br. Looking at lead iodide, I'm going to give him a -1 subscript. We're going to omit that since it's 1. And the I in iodide will give him a subscript of 2. Okay. So we've defined what a covalent and ionic bond are. We've showed how to make them from their names or their formulas. But where are they getting these names, right? So there's 2 sets of naming rules. They're different based off the type of bond. So I have a list of rules for each type. So first, you have to be able to identify what type of molecule you're trying to name. So if it is an ionic bond, right, it's because it's between a metal and a non-metal, and therefore we will name it using these types of rules. So I think I might have mentioned this in a previous lecture, but the term cation refers to a positive ion and an anion refers to a negative ion. But I just wanted to reiterate that since I use that in my naming rules. So positive charge, we've kind of seen this. It's usually listed on the left. It's the first one. So the cation charged atom goes first in the name, and it's straight up whatever its name it is on the periodic table. PT for periodic table. So Na, if we were to go to our periodic table, is sodium. Now, the anion, the negatively charged, the one on the right, goes second, except for it's ending in "ide." So chlorine now becomes chloride. If we were to look at this MnCl2, Mn is manganese. I always have to search for it on the periodic table and like double check myself that it's not magnesium. So manganese. So I really can't spell right now. So manganese is the positive ion. So it's going to retain the exact name from the periodic table. And again, chlorine becomes chloride. I don't have to mention anything about their subscripts because in ionic bonds, we know that they're always trying to get a net charge of 0, and therefore this is implied from the name. So let's go ahead and do this last one. Potassium. K is potassium. It retains the exact name from the periodic table. I didn't realize that all of these ended in chloride. It's not a great example. But other common ones, oxygen becomes oxide. Trying to think of other, chloride, oxide, fluoride. I don't think I spelled that right. Iodide, yeah. And so forth and so forth. If you most of you will have heard, and sometimes chlorine and fluoride, like sometimes we even mix up the names, and even though we're talking about chlorine not in a compound, so hopefully those "ide" endings come a little intuitive to us. So with ionic bonds, right, what happens when we have transition metals, right? So I kind of alluded to this earlier, but if the cation can carry multiple charges, i.e. a transition metal, then in the name, we need to specify with a Roman numeral what charge it was. So if I'm trying to, from this molecular formula, write the name, I would flip the charges, or flip these to get the charges. And so based on doing that swapping in reverse, I know that in this case, iron has a +3 charge. And again, here's the example of the oxide. It's the second, so iron gets to retain its name from the periodic table, and oxygen takes on the ending "ide." So here's a little bit of a tricky one because it looks like these have a subscript of 1. But we need to remember that these have been reduced. Something I had been implying, but I haven't directly said yet, is that anytime it's a +2 and a -2, and we swap, we don't write Fe2O2. We reduce them to their lowest atoms without breaking whole numbers, basically. So this is a little bit of a tricky one. We want to double check. I could slap on a +1 and a -1 here, but I need to remember, I need to double check that the non-metal is what it actually says on the periodic table. So in this case, oxygen is not a -1, it's a -2. And therefore, this iron must be acting as a +2. And so I need to specify that again in the name. So iron gets to retain its name from the periodic table with a parentheses 2 after it, and oxygen takes on the ending "ide." All right. Ionic compounds, still naming ionic compounds. Here's talking about if the ion has a if the ionic bond has a polyatomic bond. So this is a little bit easier. Still the same rules. The positive ion takes on its direct name from the periodic table, potassium. And here, I just want to go look at whatever name is listed on the polyatomic ions. And don't forget to add your bicarbonate here. So, sodium hydroxide. I'm sorry, potassium hydroxide. Here, sodium, and then where is it? SO4, sulfate. So although it's tricky sometimes identifying the polyatomic ions, naming them once we've recognized that, hey, this is something I need to go look on the table for, becomes a little bit easier because it's like, okay, now I'm just copying from the table. So here's a practice question. This is like naming ionic bonds. This is going to be like your OWL question too. So we know we're going to be naming these. I haven't introduced the covalent naming rules, but we know that we're going to be naming these off of the ionic covalent rules because when I look at the atom, or I'm sorry, the molecule, it is made up of a metal and a non-metal. So I know that this is an ionic bond, and therefore I'm going to use the ionic bond name rules. So I get to say aluminum, which is not, is it a transition metal? Let me double check. It is not. So aluminum gets to retain its name. Doesn't need any Roman numerals because it's not a transition metal. And chlorine takes on its name, but with the ending "ide." Magnesium gets to retain its name. And bromine takes on the ending bromide. Barium oxide. Okay. So again, naming using the ionic rules, and we know that because anytime we see a polyatomic ion, it's an ionic bond. So this is going to be like, again, your OWL question 2. I think it's just a different like refreshed, it's different questions, different molecules to name. So aluminum, we just remembered earlier, is not a transition metal, so it gets to retain its name with no Roman numerals. And again, this is just a matter of going to that table and looking for the name. So hydroxide, I'm not going to flip back to the table because then I think I lose my writing. But hydroxide. So here's the polyatomic ion. It's the one I added to the table. So potassium bicarbonate. Again, so I'm getting that bicarbonate from that table. Potassium, because it's the metal, so it gets to retain its full name from the periodic table. So again, here's aluminum. This is a tricky one. I honestly don't know if I have this one memorized. Let me go back. I think it's cyanate. Cyanide. Okay, so aluminum cyanide. Okay. So we've named ionic bonds. What about covalent bonds? Well, they have a whole nother set of rules. So this kind of comes back into earlier, right? I was saying we can't always know using the implied charges sometimes doesn't really relate to covalent bonds because it's not necessarily that they're giving away electrons, it's more so that they're sharing them and trying to create a full outer shell. So remember, this is between two nonmetals. And so sometimes we have to directly say how many of those atoms are in the name in order to determine the formula. Here's the rules. The name of the more metallic element, which is the one that's closer to more of the left, is first, followed by the name of the more non-metallic element, which is going to be closer to the right, is going to come second. The second nonmetal is going to have changed the ending to "ide," just like the ionic bonds. But this time, we're going to give a prefix to both of the elements based on their number of atoms. If the prefix in the first element and the first element only is mono, then we're going to omit. And so here's a list of the prefixes. They're somewhat straightforward, but I do often forget after. Basically, I always forget these ones. So let's practice using this. So the good thing about trying to determine which is the more metallic element and stuff, don't worry. Whatever element is listed first in the molecular formula, put his name first. So in this case, sulfur. The second element, fluorine, takes on the ending "ide, so fluoride. But we need to specify with a prefix how many atoms there are. So sulfur only has one atom, so it would take on the prefix mono, yet that fourth rule said that we omitted anything that had mono as a prefix, but only on the first one. So sulfur, sorry, you get to be just sulfur. But fluoride, we need to make sure we name him properly. So I believe it's hexa. See, I can just what is 6? Yes. So this becomes hexafluoride. And the full name becomes sulfur hexafluoride. It's a little bit trickier. So nitrogen gets to retain its name. Oxygen has to take on "ide. But now let's look at the prefixes. So 2 is di, so this becomes dinitrogen. 3 is tri, so this becomes trioxide. Chlorine. Now chlorine this time gets to retain his name. He doesn't become chloride because he's listed first. But oxygen has to change to oxide. Chlorine has 2, so this becomes dichlorine. And then 7 is hepta. I didn't leave myself enough space here, but hepta oxide. P is phosphorus. So it gets to keep its full name. Oxygen has to become oxide. Hexa, no, see, I told you I get mixed up. Okay. 4 is tetra. So this becomes tetra phosphorus. 6 is hexa. So hexa oxide. So water, right? We know it's H2O. We call it water, but its real name is actually dihydrogen monoxide. I think that's funny because calling water dihydrogen monoxide makes it sound really scary, even though it's just water. Fun. All right. All right, so let's practice with our OWL here. So this is specifically covalent compounds. If we weren't told that they were covalent compounds, we know to use the covalent naming rules based on the fact that this is 2 nonmetals. Again, this is like your OWL question 7. So nitrogen, I'm sorry, the first element gets to keep its name. So nitrogen. The second element has to take on the ending "ide," so oxygen becomes oxide. And then we need to give them prefixes based off of their atom number. So dinitrogen, tetra, oxide. And this is 2 different words. These prefixes are 1 word. And then, so it's dinitrogen as 1 word, tetraoxide is 1 word. I'm not doing a great job of showing you that. Okay, we already did this example earlier in the last slide. Sulfur hexaoxide. Hexoxide. For our final example here, we have 1 carbon atom and 4 fluorine atoms. So 1 atom usually corresponds to the prefix mono, but if it happens to be on the first element, we get to omit it. So we can just start off by saying carbon. Fluorine has 4, which takes on the prefix tetra. And we have to make sure we say it here because it's on the second element. So tetrafluoride, because the ending always gets changed to "ide." Now, if this was just to be CF, we'd call it carbon monofluoride. So mono is only ever used as a prefix on the second atom. All right. So moving right into chapter 4, we've made these compounds. How much do they weigh, though, right? We know how much each element individually weighs because it's directly told to us on the periodic table. But how much does a compound weigh? And this is pretty intuitive, right? It weighs the sum of all its parts, right? So if it has 2 hydrogens and 1 oxygen, it has to be the sum of that. So 2 times 1.008. I'm going to look up what oxygen is. I could theoretically say 1 times, but we know that that's a little redundant. Oxygen, depending on what periodic table you're looking at, this one happens to be 16.00, but commonly sometimes it's 15.99. And so when I multiply 2 times 1.008 and add that to then 16, I get 18.016. Now here's the kicker. What unit do I use? This on the periodic table looks unitless. But as we know, when we talked about the mole, we can either use grams per mole or AMU. I would use grams per mole. That's what's more commonly used, but both are correct. So let's go ahead and jump into a practice problem from OWL. So this is going to look like your OWL question 4. And this time it basically kind of does the same thing that we just did, but it kind of basically makes you think it all out. So it wants to know the atomic weight from the periodic table of lead, which is 207.20. And it wants you to enter all these numbers regardless of what periodic table you're looking at and how many decimal places that your periodic table decimal has. They want it to always be 2. So if the periodic table you're looking at is 207.2, make sure to slap another 0 on there, which I think was the case for mine, because the first time I did this, it told me I was wrong. Okay. So bromine is 79.90. Okay, and so now it's asking you if we were to make lead bromide, right? So if we were to make this into a compound, right, we'd swap the charges. So looking at this compound, how many ions are there? Well, for lead, there's only 1. For bromine, there's going to be 2. And in this case, saying number of ions is kind of the same as saying number of atoms. So then it wants you to, do the math systematically here. And then to get the formula weight of the entire compound, we'll then add these two together. So this was another problem I was running into. It still wants this number to 2 decimal places, because when I type it into my calculator, it just gives me 367, but they still want that. So just FYI, a hint. Okay, so here I was calling it formula weight. It's the same thing as the molar mass. Both mean the same thing. Oops. Okay. So we've talked about molecular formulas now, right? Looking at them and looking at them in their chemical symbol and subscripts for numbers. We've talked about writing them all out, right? So carbon tetrahydrogen, aka also known as methane. Next, we're going to talk about looking at the structural formula, which is a representation of the compound using the atoms and where the bonds are in relation to that, and how they're all connected. So, jump the slide. Oh, no, I didn't. Okay. So, there's dot structures, which are the elements, and it's showing this, its valence electrons, and it's valence electrons only. So let's define valence electrons real quick. Valence electrons is basically the electrons held in the outer shell, and the outer shell only. So sodium, right, if we went to the periodic table, it commonly formed a +1 charge, meaning it had 1 in its outer shell. Magnesium was a 2, aluminum was a 3, 4, 5, 6. This is just going off of the periodic table. And so we can depict those electrons using that dot method, which I was showing you and alluding to earlier, but I just want to explicitly say that now. So we have the molecular formula. And now these are different ways. Oops. Now these next A, B, C, D, these are all structural formulas. They're just different ways of depicting it. Different way of depicting CH4. Basically, this is increasing into most realistic. Can't spell. This is the least realistic, but sometimes this least realistic is the easiest to draw on paper. So just heads up. So I want to introduce this word, electron configurations. We're not going to dive too deep into it, but I just want to introduce it because it is required. But as far as I know, I haven't seen any test questions or quiz questions or OWL questions that deal with electron configurations, except for one OWL question, which I will show you and help you work through here in a second. But electron configurations are basically the same thing as an electron address. It's telling you where all the electrons in each atom are located. So I kept talking about subshells previously, right? And I've showed you a picture in the first lecture about how electrons, protons, and neutrons are in the center, and then there was electrons hanging out in the electron cloud. So each one of these rings is a subshell. The first subshell can hold 2 electrons, and each preceding subshell can hold 8. So different atoms, different elements have a different amount of subshells, depending on what they are. So for instance, hydrogen and helium can only take on a max of 2 electrons. That's because they only have one subshell. Whereas sodium has 11. So he fills up his first subshell with 2, fills up his second subshell with 8, now leaving him with 10 total. And he puts 1 in the outer one. Excuse me, I said that hydrogen has 2. He has 2 when he has a bond. He only has 1 when he's by himself. My apologies. Okay, so this is where we get that +1 charge. It's referring to the amount of electrons in their outermost shell, or their valence electrons, and how far away it is from 8. So that's why when sodium creates a bond and gives away his electron, he is still happy because underneath he has a whole nother full shell. So there's this whole complex thing to electron configurations where we can call each shell, and don't think too hard about this, S, P, D, F, etc. There's this whole big thing. We could spend a whole hour talking about electron configurations. But that's not exactly important for nurses, but I just want to introduce the idea of the subshells. So in this OWL question, it does talk about electron configurations, but I'm going to tell you how to work through that. So this is your OWL question 1. So this X, and whatever your question is, does not refer to X as in xenon. It refers to X as in like variable, solve for me, kind of as a placeholder. So your question, again, will look a little different, but it will show us the dot structure of the valence electrons, telling us how many are in the outer shell. So my example has 7 electrons in its outer shell. So if I go back a page, we can conclude based on our trend 1, 2, skip a few, 3, 4, 5, 6, 7, 8. And I apologize for the other writing. When I go back to the next page, I don't want it to erase. So since my atom that I'm solving for has 7 electrons,
it has to be in group 17. So let's go back to this page. I know there's a lot of writing. Again, I apologize. Let me erase some of this. So this first part of this question is asking you what group it's in. So for my specific one that I'm solving for, it's in group 17. If you had 2 valence electrons, you'd be in group 2. So you have to use that periodic table to figure out where you're at. So according to the octet rule, this element would be expected to form an ion with a charge of what? So my element is 1 away from a full shell, so it has a -1 charge. Sometimes, I think you've probably noticed this based on my lectures, sometimes -1 is written like this, or 1 minus, I don't know. There's a drop-down menu here. Let me look at my answer. Okay, the drop-down menu has the minus sign after the number. So next, this is where the electron configurations come into play. So it's going to ask us, it's going to tell us what period it's in, right? So if X is in period 3, yours might be a different period. The ion form has the same electron configuration as the noble gas, what? So let's go back to that periodic table. Let me erase some things. Okay. So we know my specific element I'm solving for is in group 17 and period 3. So where these intersect, my element is chlorine. Now it's asking us if the ion formed has the same electron configuration as what noble gas. So basically, whatever your element is, follow the periodic table to the noble gas of that period. So if your element happens to be sodium, your noble gas would also be argon. Okay, so if you're, oops, let's erase this. So if your element that you're solving for has a negative charge, for that specific question, asking about the electron configurations, go to the nearest noble gas, which negative charge, the nearest noble gas is going to be that noble gas that's in the same row. So mine's asking me for the noble gas argon. If the element it gives you happens to have a positive charge, you want to go to the nearest noble gas, which would be, so let's say mine was sodium. I would go to the noble gas of the row before that, so neon. It all kind of depends on what your element is. Okay. So this is a little tricky. Email me if you have questions. So let's clear some of this here. All right. So I know my element is in group 17. It has a negative charge. And so here I'm putting the nearest noble gas. So for mine was argon, and I'm just putting the chemical symbol. I don't need to spell it all out. And so now it's asking me the symbol for the ion. So we determined that mine element was chlorine. So what it's looking for is the chemical symbol with the negative charge, right? So if yours was sodium, you'd put Na+. If yours was magnesium, for this spot here, you'd put Mg 2+. Okay. So it's asking you for the whatever your element is, the symbol, and then whatever common ion it forms. Okay. I don't love that question. It honestly took me a minute to figure out what they were asking me when I was going through the L questions myself. So we introduced a little bit that each, covalently bonded atom forms different shapes, right? And we showed that, different structures. And we showed that this is the like least realistic, but this is how it's commonly depicted on paper. And again, geez, I cannot spell the word realistic. Then we had the space filling model, which is more realistic, not as realistic as the other space filling model I showed you earlier, but still great. And then sometimes this is how the space filling model is depicted on paper, where the wedge means it's going back into the paper, so backwards basically. And I'm sorry, the dash line means it's going back, and the wedge means it's coming forward at you. It's basically trying to show you this in 3D. So why the heck is it being oriented like this, right? So this is how it's oriented in space. Basically, and we'll have a lab which we get to use these little models, and I think it'll make more sense. But basically, whatever is bonded to this central atom, carbon here, they want to get as far away from each other as possible in 3D. So right now, they look like they're far away as possible, but this is only 2D, right? Theoretically, they're only 90 degrees away from each other. But remember, atoms are 3D. And so they end up kind of creating this pyramid almost. If we imagine this is like a pyramid, and then it has a topper. And this allows the atoms to get super far away from each other, or as far away as possible. And if you were to look it up, those would be 109 degrees apart from each other, which is optimal for an atom with 4 things hanging off of it. So there's this whole idea that the atoms want to get as far away from each other as possible. They want to utilize all the space that they have. So if we look at this for oxygen, so I'm sorry, water. Here's how it would be depicted on just straight up 2D paper. Here's the actual 3D model. And here's our attempt at putting the 3D model in 2D. These all are the same thing. So hydrogen, remember when we were drawing H2O earlier, hydrogen got to share a few bonds, or I'm sorry, a few electrons with oxygen. But it did still have some electrons that ended up not touching any atoms. And so those are the oxygens, the electrons that are depicted here. They're called lone pairs. So these lone pairs do end up taking space. They're just not always depicted in a 3D model. But they play a part in how the atom wants to get away from each other. So again, I didn't depict this really well, but let's use the eraser here. So there'd be this guy who's coming off here. There'd be a guy coming off into the back, which would be a lone pair of electrons. So again, remember this pyramid. And then this pair of, oh my gosh, I just clicked clear all, sorry. So there's 3D, right? There's something hanging out back there, a pair of electrons, and there's a pair of electrons up here. And they're trying to get as far away from possible as each other. So they're 109 degrees. Don't memorize the 109 degrees, but just for your reference, so you understand that the space that they're getting far away from each other as possible. So, like I said, this is how we try to depict this in this 3D model on 2D paper, is where we're showing that, hey, these hydrogens aren't 90 degrees away from each other, they are greater than 90, and these lone pairs also exist. So we could do this for a bunch of different atoms and molecules, and we'll end up with a bunch of different shapes. So CH4 that I showed you looked exactly like this model, right? This is a tetrahedral shape. H2O that I showed you was just like this, where the green were the electrons. So it ended up forming a bent shape or an angular shape. So there's linear, and there's two different types of linear if we were just to have one atom. So let's say that oxygen was bonded to itself. That'd be an example of linear. Here's an example of linear, but with 3 bonds. So a good example of that is CO2. Has those double bonds. I don't have a good example for triangular planar off the top of my head, but basically here, the farthest they can get away from each other is 120 degrees. And this ends up being, as you might, from the name planar, this actually ends up looking the same in 2D as it does 3D because it stays in one plane. Very interesting. Whereas the rest of these are all 3D. There's trigonal pyramidal, which kind of looks like tetrahedral, only the top guy is a lone pair of electrons. And it basically just is that base of that pyramid. So you might be a little confused, and that's okay. This is just an introduction. We'll revisit this later. But I needed to introduce it before I introduce the next idea of polarity. So what is polarity? We might have heard of things being polar or nonpolar. So that's describing its polarity. So polarity is the separation of electric charges in a molecule that leads to having a dipole, which is a negatively charged end and a positively charged end. So polarity is all based off of the trend of electronegativity. So if there's one trend to remember, it's electronegativity. So this periodic table, if you notice, it's like got skyscrapers coming out at us. It's a periodic table where they've assigned values to electronegativity. So you see we increase as we go to the right and increase as we go up, just like the trend of electronegativity. And the noble gases do not participate in this trend, again, just like the trend of electronegativity. Only this time we've assigned values. We've assigned values to the electronegativity, and I'm abbreviating electronegativity as EN. So, like we talked about earlier, electronegativity is basically saying how bad you want those electrons. Where a higher number means you want it more. So this definition of polarity talked about an electric dipole moment. What the hell is that? So when we create a bond, so here's the bond for water. There's moments in which, and where this is going back to the hot potato, there's moments in which one atom spends more time with those electrons that are being shared. And this is a dipole moment. So this is all based off these random values. So if we notice, ignore these numbers. I don't know what these numbers are trying to tell us, to be honest. This is just a picture I pulled from the internet. So oxygen has a value of 3.5 and hydrogen has a value of 2.1. So this means that oxygen wants those electrons more than hydrogen does. He ends up kind of playing that tug of war, and he's a little bit stronger. He wants it more badly. And he ends up holding on to those electrons for just a little bit more time than hydrogen does. And so this ends up creating a little bit of a negative space. Ignore these Greek symbols. A negative, there's more electrons hanging out with oxygen, and it creates more of a negative charge on this end of the molecule, whereas hydrogen is spending a little less time than oxygen is, creating more of a positive. So those are dipoles. So sometimes we depict this as a little arrow with a plus sign on one end and an arrowhead on the other, where this is the more positive end. And this is where the electrons are going. Therefore, the more negative end. And again, this is all based off of that electronegativity values. Don't memorize the values or anything. Memorize the trend. That will be useful. So I like this picture here because it shows the more it shows them based off their size, and then they're more negative based on the arrows. So if we were to look at the table, hydrogen has electronegativity value of 2.1, carbon 2.5, right? But if we were just to follow the trend, we know that carbon is the more electronegative atom. So in a bond, this would be the more negative end. This would be the more positive end. If we were to do the same thing for boron and fluorine, fluorine is the most electronegative atom. He's always going to hold on to the electrons more. And boron is going to be slightly positive. So I've showed you this in terms of H2O as a whole molecule, and then into just each separate bonds, right? So there's dipole moments for each bond in a molecule. So here I showed you that those same arrowheads for oxygen, I'm sorry, for H2O, right? But there's this whole idea that we can draw an overall dipole for the entire molecule. And so that's what this arrow is depicting. If we were to basically sum these arrows together, for the most part, the electrons are hanging up by the oxygen. If we were to look at CO2 here, oxygen is the more electronegative atom. If we were to try to draw an overall dipole, though, there wouldn't be one, because each of these are going perfectly in the opposite direction of each other at the same strength too, mainly because it's the same atom. So determining overall dipole moments is what helps us determine polarity. So we showed that these dipoles cancel each other out. And so there was no overall dipole moment. And therefore, this molecule is nonpolar. We showed that H2O ends up having this overall dipole moment of upwards. And so this molecule exhibits polarity, or it's polar. Now, I like this example because they are going opposite directions, but they're different atoms, so they have different intensity. And so the overall dipole moment ends up going more to the left here. So again, if there is an overall dipole moment, no matter how big or small, the molecule is polar. So you're probably like, Kayla, you told us that shape was involved. Yes, shape is involved. And we saw that in oxygen, in the example of H2O, right? I showed you the diagrams in which it was bent because the shape contributes to where those dipoles are pointing, right? Because those atoms want to get as far away as possible from each other. So that's how they're going to look in space. And then they're going to, yes. So how the direction in which we draw those dipoles depends on their shape. So I kind of already touched on this, but polar is having an electro or magnetic polarity. Basically, it has an overall or net dipole. So H2O is polar. Nonpolar molecules have no overall or no net dipole. So a good example of this is CH4. And so when you're looking at this specific diagram, it might be a little confusing, but you have to remember this is 3D, right? So this guy who's pointing down is going to cancel out these three that are pointing in this direction, if that makes sense. So think about if this was in 3D, right? I said this bottom is kind of like a pyramid. It's not a great drawing of a pyramid, but if we were to think about the dipoles on the pyramid alone, the sum of them would end up pointing up, right? Well, that sum is equal to the one pointing down. So let's look at an example here. So spoiler alert, this is an example of a polar molecule. So if we were to go back to the periodic table and look at that trend, right? The electronegativity trend. Fluorine is the most electronegative, and nitrogen would fall somewhere over here, meaning it has less electronegativity. And so all the dipoles would be pointing towards the fluorine atoms. So let's think about the shape, right? This has a central atom, and then it has basically, including the lone pair, 4 things connected to it. So those atoms are like a pyramid on the bottom with a little antenna on top. So overall, the net dipole is pointing down because these atoms want to get as far away from each other as possible. So they go to the ends of these pyramids. And they also want to get far away from possible as the electrons. But the electrons do not contribute to the overall dipole moment. So because it has a net down dipole, this ends up being polar. Here's an example of a nonpolar molecule. So if we were to look at the periodic table and look at the trend of electronegativity, oxygen would be more electronegative than carbon. And these arrows would be of the exact same intensity because it's the exact same CO bond, basically. And there's only two groups hanging off of this central atom, meaning that it would be linear in shape. And so that these two dipoles end up canceling each other out. And so there is no net dipole, meaning that this molecule is non-polar. So let's look at your OWL question 6, which is asking if something is polar or non-polar. And so in your actual OWL, you can grab this little guy and you can move him around. I'll tell you right now that this is the triangular planar, meaning that all three of these guys are in the same plane. And so they're all the same atom. All are going to point towards the fluorine because fluorine is the most electronegative atom. And they're all pointing in opposite directions of each other, meaning there's going to be no net dipole. Meaning that BF3 is nonpolar. So PCl3, pretty similar, only it has this downward pyramid kind of shape. And if you were to be able to grab it with your mouse and spin it around, you'd be able to see that. And so if we were to look at the periodic table, Cl would be the more electronegative atom, meaning that all the dipoles would point towards all the Cls. And because this is not in the same plane, like it is up here, there's a net dipole that's pointing down. So this atom is polar. So polarity is a very complex thing. And I wish we had more time to talk about it because I'm imagining you're a little confused. Unfortunately, we don't have more time to talk about it. But if you have more questions, visit me in office hours. Okay, so I have one more slide to end chapter 4. Now this slide I found very fun to make, if you will, because there's this hotly debated topic in chemistry. Which type of bonds are stronger than each other? Is it ionic or is it covalent? So if you were to go Google this, you're going to get about 50-50 results. Some scientists believe that covalent is stronger. Some scientists believe ionic is stronger. I personally was taught that covalent was stronger. And I think of covalent as being like a chain link like this, where they're sharing electrons. And I kind of think of ionic as being these little, I don't know if you remember having these magnets, if your kids had them, or if you had them as kids, where you can pull them apart, right? But they're going to find their way back to each other. That's always how I thought of bonds. So I was taught that covalent bonds are stronger than ionic. This textbook is going to tell you that ionic bonds are stronger. So if you come across a exam question that asks you which one is stronger, for the purpose of the exam, ionic bonds are stronger. I think I personally disagree, but that doesn't matter. I didn't write the exam questions. So, ionic bonds are stronger according to this textbook. That wraps up chapter 4.